Hello and welcome everyone. My name is Markus Hofbauer. I am from the Chair of Media Technology at the Technical University of Munich. Today I will introduce you TeleCarla, an open source extension of the CARLA simulator for teleoperated driving research using off-the-shelf components. Teleoperated driving can be a possible fallback candidate for autonomous driving. Whenever the autonomous vehicle encounters some problems it cannot handle on its own, a human operator can dial in and resolve the situation from remote. A regular teleoperation setup consists of a vehicle and an operator workstation. The vehicle transmits sensor information over a mobile network to a remote operator. The operator perceives the situation and returns the control commands back to the vehicle. On the right you can see such a teleoperation setup. Here the authors initially proposed their setup and extended it over the years with additional features to improve the visualization or operator performance. However, when starting the development on teledriving, there is so far no easy accessible solution. As always in the automotive development, there are expensive requirements such as the vehicle. Similar to autonomous driving, where the development starts in simulation, we want to provide an easy solution to set up teledriving. Existing driving simulator solutions that ship with a driving cockpit are still very expensive, commercial, and not open for customization. The main reason is that their focus is on in-car driving. For instance, the authors of the before-mentioned teleoperation setup use such a simulator and have to use screen-grabbing software to access the camera data which is required for the transmission. TeleCarla addresses this problem. It is a customizable open-source framework for teledriving which extends the open-source CARLA simulator and only requires low-cost, off-the-shelf gaming hardware. So at first let's have a look at the CARLA simulator our extension is based on. CARLA is an open source simulator which is specially designed for autonomous driving research. It provides already various sensor types, many assets, and is supported by a large community. CARLA itself is already designed in a client-server architecture which makes it very flexible. However, CARLA is not directly usable for teledriving as the client-server communication so far is only transmitting raw sensor data. But with all the before-mentioned benefits, it is very suitable as a vehicle simulator to be extended for teledriving. So let's start with our hardware setup. We use a standard powered PC which has only the requirement of a GPU in order to run CARLA. For visualization, we use 3 regular displays. The control commands can be entered either by keyboard or the gaming wheel and pedals. To improve the driving feeling, we use additionally a gaming seat. Seat, wheel and pedals are together below 500 euros. The architecture of TeleCarla is based on the robot operating system ROS. On the server side of TeleCarla, both the CARLA server and clients are running. This allows for using all existing CARLA features such as controlling the weather, managing the other traffic, or running dedicated scenarios. The communication between TeleCarla and CARLA is via the ROS bridge. With the ROS interface, TeleCarla could be even used with any other simulator or real vehicle that provides a ROS interface. There are 2 main parts in the TeleCarla server. The GStreaming server, which uses the GStreamer multimedia framework for transmitting the video stream, and the RPC server, which receives the control commands from the human operator. As one challenge in teleoperation are variable network conditions, we provide an adaptation interface to adapt the video stream to the current network conditions. This interface allows for changing the target bitrate and frame rate of the video encoder online. On the client side, the video stream is received, decoded and shown to the operator with our user interface. The user interface also reads the control commands from the input device which are sent back to the server using the remote process communication protocol. The layout of the user interface can be customized in a configuration file in a matrix-like manner. Here we show an exemplary user interface with a 6-camera setup. 3 front-facing camera views are shown in the bottom row, whereas 3 rear-facing views are shown in smaller size in the top row. The left free segment between 2 rear-facing cameras shows the vehicle status information such as current speed, acceleration, steering angle, etc. The right segment so far is empty but could be filled, for instance, with a bird's eye view of the vehicle or a map view. New visualization components can be just implemented and integrated into the existing user interface. To validate that TeleCarla is suitable for the requirements of teleoperated driving, we performed a small user study. For this, we evaluated 3 different driving modes in 6 scenario categories. Details on the scenarios will follow on the next slide. Having multiple scenarios on the same category is required to avoid that the participants learn specific routes and breakpoints. Every participant evaluated a single scenario of every category in every mode, so in total 18 scenarios. The 3 modes to be evaluated are named Local, CARLA and TeleCarla. To avoid influences caused by the representation, all 3 modes use the TeleCarla-User Interface, as the focus of this evaluation is on the communication part. The local mode simply means local driving in the CARLA simulator without any additional delay due to transmission between 2 machines and without compression. This acts as a baseline. The CARLA mode simulates teleoperation by connecting a CARLA client to a CARLA server on a second machine. This means there will be an additional delay caused by the remote connection, but no compression as CARLA transmits only raw data. The TeleCarla mode uses our GStreamer pipeline in constant bitrate encoder mode with a target bitrate of 2 megabit per second. This means there is no quality reduction due to the compression and additional delay from the transmission and compression. As mentioned before, all participants evaluated 3 scenarios in the 3 driving modes for all 6 categories. The 6 scenario categories are regular driving tasks and are predefined scenarios of the CARLA scenario runner. These scenarios are as follows: a dynamic object that is crossing the street, following a vehicle which will brake due to an object on the street, turning right at a signalized junction, surpassing an obstacle on the opposite lane with oncoming traffic, avoiding a stationary object, and turning right at a signalized junction with oncoming traffic. Here we present the overall results of the scenario evaluation in terms of scenario duration, collision rate, the bitrate required for the transmission, and the frame rate. The local baseline mode runs at a frame rate of 20 Hz. There is no bitrate as the entire setup runs on a single machine, so without any transmission between 2 machines. On average, the user required 41 seconds to finish a scenario and produced in 6% of all cases a collision. The CARLA mode produces a large transmission rate of 69 megabits per second due to the raw sensor transmission. This causes a low frame rate of about 3.6 Hz, which results in a higher scenario duration and increased collision rate compared to the baseline. The TeleCarla mode is able to run at 20 Hz at a target bitrate of 2 megabit per second. The duration and collision rate is larger than for the baseline, which can be explained by the additional delay of the transmission. However, the higher frame rate results in a better performance and scenario duration compared to the CARLA mode. Here we take a closer look at the performance on specific scenarios. In the 3 bar plots we visualize the scenario duration in blue and the collision rate in orange for the 3 modes local, CARLA and TeleCarla. The local mode on the left again acts as the baseline for the different scenarios. The CARLA mode has a very high collision rate, especially for the scenarios 3 and 4, which are the turning at a signalized junction and the obstacle avoidance with oncoming traffic. This can be explained due to the low frame rate of 3.6 Hz, which is critical for steering intensive tasks. The TELECARLA mode performs better on the simple turning task, but still has a high collision rate on the avoidance scenario. This can be explained due to the introduced delay, which increases the difficulty of highly dynamic scenarios. This brings us to the conclusion of this talk. We addressed the problem that there is no easy accessible framework for teleoperated driving research. So far, either a real vehicle or expensive simulation hardware had to be used. Our contribution is TELECARLA, an open source extension of the CARLA simulator as a basic framework for teleoperated driving research. The TELECARLA architecture is based on ROS to provide common used interfaces and to run as a modular and scalable software. This would even allow to use TELECARLA for any other simulation or real vehicle that provides a ROS interface. Further, we use the open source GStreamer multimedia framework for the video transmission part. Finally, we performed a small user study to show that CARLA is by design and scope not directly suitable for teledriving, and TELECARLA can be used to fill this gap. With TELECARLA, we provide an open source framework for teleoperated driving research. The source code is available on GitHub under the URL noted on the slide. We are actively working on the TELECARLA ecosystem and try to support future CARLA releases. If you have any problem or identify some errors, don't hesitate to contact us or directly open an issue in GitHub. We welcome collaboration, so feel free to discuss new features with us or directly open a pull request on GitHub.